I've been wrong before. Not often, but enough times to know what it feels like. There's a particular sensation when you realize the picture you've been carrying in your head, the one you were so sure about, doesn't match what's actually out there in the world. It's not embarrassment, it's not panic, it's something closer to awe. Because if the picture is wrong, that means reality is more interesting than you thought. And I have always found reality more interesting than anything I could invent. This is the story of the moment I understood that. Really understood it. Not from an equation, not from a conference, from a woman named Vera Rubin, and from the galaxies she refused to stop looking at. I was in Pasadena, Caltech, home. I had just come back from a run of lectures that had left me tired in the way that only too much talking can leave you tired. I was not in the mood for more physics. Then a colleague showed me a paper. He set it on my desk without saying a word, just left it there and walked out. The paper was by Vera Rubin and Kent Ford, published in 1970, though I had not paid it the attention it deserved. It was about the rotation of the Andromeda Galaxy. I picked it up. I read the first page, I read the second page. Then I went back and read the first page again, because what Vera Rubin had found did not make any sense. And when something doesn't make any sense in physics, one of two things is happening. Either someone has made a mistake, or the universe is telling you something you do not yet know how to hear. Let me explain what the paper was supposed to show. When you look at a galaxy, a spiral galaxy, the kind with the pinwheel arms, you expect a certain pattern of rotation. Think about our own solar system. Mercury, close to the sun, moves fast. Mars, further out, moves slower. Neptune, way out at the edge, moves very slowly indeed. This is exactly what you expect. The closer you are to the massive object at the center, the faster gravity pulls you around it. This is just Newton. This is just Kepler. We have known this since the 17th century. We assumed galaxies worked the same way. Of course we did. Why wouldn't they? Stars near the bright center of a galaxy, where most of the mass is concentrated, should orbit fast. Stars out at the edges, far from the center, should orbit slow. This is the rotation curve. Plot the speed of orbit on one axis. Plot the distance from the center on the other. You expect a curve that rises near the middle and then falls off slowly as you move outward. That's what the curve should look like. That is not what Vera Rubin found. What Vera Rubin found was flat. The curve didn't rise and fall. It rose near the center, as expected, and then instead of falling, it stayed flat. Stars at the outer edges of the Andromeda Galaxy were orbiting just as fast as stars near the center. Not a little bit as fast. Just as fast. She measured it. She measured it again. She measured it again and again. Vera Rubin was meticulous in a way that I have always respected more than brilliance. Brilliance is exciting. Meticulousness is how you find out what is actually true. She checked the instrumentation. She checked the calibrations. She went back to the telescope. The data kept saying the same thing. Stars far from the galactic center were moving far too fast. If those stars were only subject to the gravitational pull of the visible matter in the galaxy, the stars and gas and dust you could see, they should be flying off into space. They were going too fast to be held by what we could see. Something was holding them. Something with mass. Something we could not see. I put the paper down. I walked outside. I walked around the Caltech campus for a while. This is what I do when something is bothering me. I walk and I let the problem sit in the back of my head without forcing it, because I knew what the data meant. The data was clear. Vera Rubin's measurements were not sloppy. They were not approximate. They were the work of someone who had looked at this problem longer and harder and more carefully than almost anyone else alive. The data meant there was mass in those galaxies that we couldn't see, and the amount wasn't small. You couldn't explain the rotation curves with a small correction. A few % of hidden material wouldn't do it. The math said the visible matter, everything we could detect, everything we could photograph, everything that emitted or reflected any kind of light was maybe a quarter of the total mass needed, maybe less. The rest was something else, something that had mass, something that responded to gravity, but something that did not interact with light at all. We had no name for it yet. Fritz Zwicky, a Swiss astronomer who worked at Caltech and who was considered eccentric, which at Caltech takes some doing, had noticed something similar decades earlier when he looked at clusters of galaxies. The galaxies in the clusters were moving too fast. Zwicky had said there must be missing mass. He called it dunkel materie, dark matter nobody had taken him very seriously. Zwicky was prickly and difficult, and had a habit of insulting everyone in range, which is not a good strategy for getting your ideas accepted. But now here was Vera Rubin, careful, thorough, systematic Vera Rubin, saying the same thing, with data. I should tell you who Vera Rubin was, because the story of her data cannot be separated from the story of what it cost her to collect it. She became interested in astronomy as a child. She grew up in Washington, D.C., and she would push her bed to face the window so she could watch the stars at night. She kept notebooks. She tracked meteor showers. She was absolutely certain by the time she was a teenager that she wanted to study the sky for the rest of her life. She applied to Princeton's graduate program in astronomy. They sent her information back. Women were not admitted to the program. Not enough interest, she was told. Not enough ability. Not enough of the right kind of mind. She went to Cornell instead. She wrote a master's thesis suggesting that galaxies might be rotating around a larger center, that the universe might have a large-scale structure we hadn't mapped yet. She was right about this. She was decades ahead of the field. When she presented this work at a meeting of the American Astronomical Society, one of the most senior astronomers in the room publicly dismissed it, called it unlikely. She was 22 years old. She was also, that year, pregnant. She was not allowed to attend certain conferences because some institutions did not permit women. She had to submit papers under her husband's name to be taken seriously at some journals. I am telling you this not because it is unusual for the time. I am telling you this because it is usual for the time, and because I want you to hold it alongside the quality of what she produced. She produced that data anyway. When Vera Rubin published her rotation curve data, not just for Andromeda, but eventually for dozens of galaxies, galaxy after galaxy, showing the same flat curve, the reaction from the physics community was not exactly triumphant. There was skepticism. There were alternative explanations proposed. Maybe her measurements were off. Maybe she had misunderstood the dynamics of galactic gas. Maybe the issue was with how gravity worked at large scales. Maybe Newton needed modification. That last possibility was taken seriously by some people. Modified Newtonian dynamics, it was called. MOND. A different way of calculating gravity at very low accelerations. It could explain some of the data, not all of it, but the dark matter explanation kept fitting. Not just for rotation curves, for the way galaxy clusters behaved, for the way the universe's large-scale structure had formed, for the way light bent around clusters in ways that required more mass than you could see. The evidence accumulated. It accumulated the way real evidence accumulates, not in a single dramatic moment, but piece by piece, each measurement pointing the same direction. Here is the thing that I kept coming back to. Not the evidence. The evidence was becoming hard to argue with. The thing I kept coming back to was what it meant philosophically, what it meant for physics as a discipline, what it meant for how we think about knowledge. We had built an entire science of the universe based on what we could observe. We measure light, we measure radiation, we measure particles. Everything we know about the cosmos, we know because something interacted with our instruments, because something made a photon hit a detector, because something left a track. Dark matter, if it is real, does none of these things. It does not emit light. It does not absorb light. It does not interact with our instruments in any direct way. The only thing it does, the only sign it leaves, is gravity. And this means that everything we have ever observed, every star, every galaxy, every nebula, every quasar, every cosmic structure we have ever mapped, is not most of what is there. We have been studying the froth on the surface and calling it the ocean. Think about that. All of astronomy, all of cosmology, all of the work of every person who has ever turned a telescope toward the sky and spent a life measuring and cataloging and understanding. We have been studying the minority of the universe, the luminous minority, the part that shines. The rest, the majority, the dark majority, has been sitting there the whole time, invisible to every instrument we have ever built, holding the galaxies together, shaping the structure of everything, silent. I am a physicist. I like to understand mechanisms. I don't just want to know that something happens. I want to know how. I want to see the picture. I want to understand what is actually going on at the level of particles and forces and interactions. So the question I could not stop asking was, what is it? Not is dark matter real? The data was too good for that question. Vera Rubin and the people who followed her had asked that question and answered it about as well as such a question can be answered. My question was, what is it made of? And here is where I have to be honest. I didn't know. Not in 1975. Not before I died in 1988. Not as of any conversation I have been part of. Nobody knows. We have candidates. We have particles that the theory of supersymmetry predicts. WIMPs, weakly interacting massive particles. We have axions. We have sterile neutrinos. We have primordial black holes. We have built enormous detectors and buried them deep underground, deep enough that cosmic rays can't reach them. And we have waited, very patiently, for a dark matter particle to bump into an atomic nucleus and leave a tiny trace of energy behind. We are still waiting. Every candidate we have proposed, every experiment we have designed, has either come up empty or is still running. The universe is in no hurry to explain itself to us. I want to tell you what Vera Rubin herself said about the fact that we couldn't identify what dark matter was. She was not troubled by it, or rather she was interested by it, which for a scientist is the opposite of troubled. She said more than once that she hoped dark matter would turn out to be something completely unexpected, something nobody had thought of, something that would require new physics, not just a new particle in the existing framework, a genuinely new kind of thing. I understood that feeling entirely. I have spent my whole scientific life hoping that the next layer of reality would be stranger than the last, and it always has been. Quantum mechanics is stranger than classical physics. Quantum electrodynamics is stranger than quantum mechanics. Every time we have dug deeper, the world has turned out to be weirder and more surprising than we had any right to expect. There is no reason to think this process is over. Vera Rubin believed it wasn't over. She believed she had found the edge of what we knew, the place where the map runs out and the territory continues. She was right, but here is the thing that actually disturbed me. Not the existence of dark matter, not the fact that we can't identify it, not even the scale of our ignorance. Though that is staggering, what disturbed me was a question of method. Physics works by testing predictions. You build a theory. The theory predicts something measurable. You go measure it. If the measurement matches the prediction, the theory survives. If it doesn't, the theory dies. This is the whole game. This is what makes physics different from philosophy. We test things. We measure things. Reality is the judge. Dark matter presents a peculiar challenge to this method, because we built the dark matter hypothesis from the rotation curves, from Vera Rubin's data. We said there must be matter we cannot see because the visible matter is not enough. This is a reasonable inference, but then we go looking for this matter, and we don't find it, and then we don't say therefore dark matter doesn't exist. We say therefore our detectors are not sensitive enough, or the particles are lighter than we thought, or they interact more weakly than we expected. We adjust the hypothesis. We keep looking. This is also reasonable. We should keep looking. The inference from the rotation curves is strong, but I find myself asking, at what point does a hypothesis become unfalsifiable? At what point does the absence of detection become evidence that we are looking for the wrong thing entirely? I do not have an answer to this question. I want to be clear about that. I am not saying dark matter is wrong. The gravitational evidence is overwhelming. I am saying the question of what dark matter is might require us to think in ways we haven't thought yet, to ask questions we haven't asked, to accept that the universe does not owe us an explanation in terms of the particles and forces we already know about. Vera Rubin said something once that I have not been able to shake. She said that in her experience, every time astronomers had been certain that they understood the universe, they had been wrong. Not partially wrong. Not missing a small correction. Wrong about something fundamental. She said the history of astronomy is a history of the horizon receding. Every time we think we have reached the edge, we discover we are standing in the middle. I think about this in relation to my own work. I spent years working on quantum electrodynamics, the theory of how electrons and photons interact. It is the most precisely tested theory in the history of science. The agreement between theoretical predictions and experimental measurements is so accurate, it is like predicting the distance between New York and Los Angeles to within a hair's width. I was very proud of this, but quantum electrodynamics describes something like 1% of the matter in the universe, maybe less. The electrons and photons, the things I spent my career understanding, are the minority, the glowing, visible, luminous minority. The rest, the dark majority. We don't have a quantum electrodynamics for that. We don't have a standard model for that. We don't have, so far as I know, a single equation that correctly describes what dark matter actually is. We have gravity. We have the shape of its gravitational influence. We have the map of where it must be from how it bends light and pulls stars, but we do not know what it is. Vera Rubin spent decades staring at galaxies and telling us this, telling us the story was bigger than we thought, telling us the cast of characters was larger, telling us we were missing something. Most of the universe is made of something we cannot identify. Think about that sentence. Most of the universe. I have thought a lot about what it means to not know something. There are two ways to respond to a gap in your knowledge. The first is to pretend the gap is smaller than it is, to paper over it with confident-sounding language, to say we understand the outline and the details will follow, to wait for someone else to fill in the blank. This is the comfortable response. It is also how fields stagnate. The second is to stand at the edge of what you know and stare into the dark and say, clearly and without embarrassment, I do not know what is out there. This is what Vera Rubin did. She found a gap, and instead of minimizing it, she spent her career making sure everyone understood exactly how large it was. She measured the flatness of those rotation curves with the kind of precision that leaves no room for argument. She made the problem undeniable. She did not solve the problem. She made it real. And this, I want to say this carefully, because I mean it completely. This is one of the hardest and most important things a scientist can do. It is easier to solve a problem that has already been properly identified than to identify the problem in the first place. It is easier to find what you are looking for than to notice what you didn't know you needed to look for. Vera Rubin noticed. She sat at the telescope, often the only woman in the building, sometimes the only woman who had ever been in that building. And she noticed that the galaxies were not doing what they were supposed to do. And instead of assuming she had made an error, she assumed the universe had something to say. That is what good science looks like. That is what the courage to follow data looks like. Even when the data makes no sense, even when senior colleagues tell you it's unlikely, even when the journals are resistant and the conferences are closed and the institutions have decided, without looking at your work, that someone like you probably doesn't have the right kind of mind, she kept looking anyway. Vera Rubin died in 2016. She was 88 years old. She never received the Nobel Prize. Many people believe she should have. Many people believe it is one of the more glaring omissions in the history of that award. She spent the last years of her life, as she spent all the years before, looking at galaxies, measuring rotation curves, writing papers, arguing for the importance of what she had found. And dark matter, whatever it is, wherever it hides, whatever particles it is made of, or is not made of, dark matter is still out there, still holding the galaxies together, still shaping the structure of the universe, still undetected by every instrument we have pointed at the sky. The problem she made real is still real. If you go outside on a clear night and look up, and I have always believed you should do this as often as possible, the light you see is the luminous minority, the stars and galaxies that glow, the fraction we have names for. But around every one of those points of light, and between them, and filling the vast dark spaces between the galaxies, there is something else. Something heavy with gravity. Something invisible. Something we do not understand. Vera Rubin found it. She spent her life telling us it was there. And the universe, patient, silent, dark, is still waiting for us to figure out what to make of it. The horizon is still receding. And I find that genuinely one of the most beautiful things I have ever encountered.